Hello, this is Marcus Crawford. This is part one geochemical data experiment presentation. The objective of this project is to analyze and compare geochemical data from two datasets acquired from the University of Missouri Research Reactor. Um, they have an online database, and we were able to find two out of the whole entire thing that pertain to chert. To better understand their elemental composition and identify any significant differences or similarities. The end goal here is to employ some of the methods that were covered this semester in this course. The work environment is Google Colab, and we'll be experimenting using the Python work environment, extracting and analyzing this data using Pandas, GeoPandas, NumPy, Matplotlib, Seaborn, and sklearn. Our objective is to compare these data sets, and they'll be referred to in this presentation as DF1 and DF3. As far as where the data comes from, one set, DF1, pertains to Michael Quing, and his research paper is titled Geochemical Characterization of Tecovas and Alabate Source Samples. DF3 is neutron and activation analysis of stone artifacts at Paleo Crossing by Matthew Bollinger. The problem here is to develop more accurate methods of distinction to source this material to presumed geologic feature that might give off a particular elemental signature, like, say, out of the ordinary or higher levels of iron or titanium, whatever element that may be. Can we come up with a method of distinction and being able to visualize if this is meaningful? So looking over here at the beginning of this presentation, here we first have to mount the drive. So this here is stored right there. Set up mounting this, and this is the pathway to the data sets, and this is where they're defined as DF1 and DF3. Just to give you an idea of what the data looks like, this is what it looks like in its raw form, and this is what we're looking for. This element list, which is parts per million of 32 different elements. Here's the coordinate systems. Here's the other data set. Anyways, continuing down, we're executing here a basic exploration of our data set using pandas, and just kind of looking at it at first, trying to streamline it at this point. Checking if element in common in both data frames. And here we're finally getting to what we're looking for, is comparing the elemental list. At this point down here, I'm doing some descriptive statistics, just kind of trying to see if it can execute these functions to then move on to what we're looking for, which we get to that here, down here a little bit further. So an issue that I had, and this was a recurring theme that I had to create a patch for every test every time I ran it, was this missing NaN value for zirconium in one of the data sets. It was present in one of them, but not in the other one. Pause. Continuing on. So once we got everything cleaned up, the following what we did was use kernel density estimation to plot all the different elements out and kind of look over and get a visual on some of the plotted distinctions. And this is how we accomplish this, and this is the data set. So if we look through here, I think we can pull out a clear visual distinction. Here's a difference, the Ubidium. This one I think is rather significant as well. And this is going to be for calcium, hafnium, and tantalum. I think it's Ta. Calcium. Anyways, KDE is used to estimate the probability density function of a continuous random variable. It's a non-paradigmatic way to estimate distribution of a variable, according to Silverman, 1986. A kernel is a mathematical function used in KDE to assign weights to data points. For each data point, the kernel function is centered on the point and contributes to the overall density estimate. The contribution from all data points are summed to produce the density estimate. For each data point, the kernel function is centered on that point and contributes to the overall estimate. The contribution from all the data points to produce the density estimate. KDE plots were generated for concentration of each element in both data sets, DF and DF1 and DF3. So in conclusion, the project began with the acquisition of distinct data sets by Michael Quigg and Bollinger's two distinct studies. This involves standardizing column names, handling missing variables, ensuring that the data types were appropriate for analysis, and then we did a statistical computation of both that kind of gave descriptive statistics, and then we went on to implement KDE to give out a distinction. If you look over here, this is the same thing except it's plotted differently. And as this is just part one of this presentation, I'll go into in part two, which will be part 253.16, trying to accomplishing a PCA analysis, k-means, and then geospatial modeling of the data. Thank you.